All right, everyone, get ready because today we're going deep into the world of VEGFA.
VEGFA.
That's vascular endothelial growth factor.
Quite a mouthful.
It is, but don't worry, we're going to break it all down today using this awesome article from Assay Genie.
It's a good one.
It is called Vascular Endothelial Growth Factor A, VEGFA, a cornerstone in angiogenesis and beyond.
Catchy.
Right. So you might be thinking, VEGFA, what is that?
Sounds kind of sci-fi.
It does, but honestly, it's way cooler than sci-fi because this stuff is happening inside your body right now.
All the time.
Yeah, think about how your body builds all those blood vessels.
An incredible network.
Exactly, and not just when you're growing up, but also when you need new ones, like when you get injured or something.
The body is amazing.
It is, and VEGFA is a VIP in that whole process.
You could say it's like the maestro of angiogenesis.
Maestro of angiogenesis. Okay, I like that.
That's the fancy term for making new blood vessels.
Okay, so it's conducting the whole blood vessel construction process.
But
But what is VEGFA exactly? Like, what are we actually talking about here?
at its core, it's a signaling protein.
Signaling protein.
Yeah, so it acts like a conductor guiding the growth of new blood vessels from the ones that are already there.
So it's like the body's way of building its own plumbing system.
You got it, a very intricate plumbing system.
But how does it know where to build these new vessels? Like, is there a map or something?
Well, you need a blueprint.
Right.
And in this case, the blueprint is the VEGFA gene,
The VEGFA gene.
which lives on chromosome 6.
Chromosome 6, okay.
And this gene holds the instructions to create the VEGFA protein.
Okay, so the gene is like the instruction manual and the protein is the actual worker doing the building.
Exactly. But here's where it gets really interesting. The VEGFA protein isn't just one size fits all.
Wait, are you telling me there are different types of VEGFA?
You got it.
Okay, my mind is blown.
It's like having a toolbox full of different tools.
Okay.
We call these different types isoforms.
Isoforms.
And each one has unique properties.
So it's like VEGFA has a whole wardrobe of different outfits and each outfit gives it special powers.
That's a great way to put it. Each isoform interacts differently with receptors on cells,
Receptors.
which influences which biological processes they're involved in.
Okay, this is getting complex.
A bit, but it's fascinating.
It is. Okay, so give me an example of one of these VEGFA isoforms.
Sure, one of the most important ones is VEGFA165.
EGFA165, that's going to be on the test later, everybody.
This one is the most abundant and active isoform. It's like the star of the show.
The Beyonce of VEGFA.
You could say that.
So what does VEGFA165 actually do?
It plays a major role in angiogenesis and also affects vascular permeability.
Vascular permeability. What is that?
It's basically how easily things can move in and out of those blood vessels.
Oh, so it's like controlling the border traffic for the blood vessels.
Exactly.
Wow, so we're starting to see how this VEGFA is like this multi-talented molecule. It builds blood vessels. It helps regulate what goes in and out. Are there any other things it does?
Oh yeah, lots. VEGFA is a busy molecule.
Okay, give me another one.
It's key for wound healing.
That makes sense.
Yeah.
You need new blood vessels to repair damaged tissue.
Exactly. And here's a surprising one. It also plays a role in the female reproductive cycle.
Hold on. VEGFA is involved in wound healing AD, the reproductive cycle.
It is.
This molecule does it all.
It's a jack of all trades.
But what tells it when to spring into action? Like, how does it know when and where to do all these things?
Well, the production of VEGFA is actually controlled by oxygen levels.
Oxygen levels.
It's like a built-in supply and demand system.
Okay, now you've got me really curious.
So imagine a situation where a tissue isn't getting enough oxygen,
Okay.
maybe because there's a blockage or something.
Right.
Our cells have this amazing protein called HIF1,
HIF1.
which acts like an oxygen sensor.
So it's like the canary in the coal mine for oxygen levels.
Exactly. When HIF1 senses that oxygen is low, it triggers a chain reaction that leads to more VEGFA production.
So more VEGFA, more blood vessels, and more oxygen delivered to where it's needed.
Precisely. It's a brilliant system.
It is, and it's all thanks to VEGFA. This tiny molecule is working tirelessly behind the scenes.
Keeping us alive and functioning.
It's like the unsung hero of our bodies.
Absolutely. But here's where things get a little complicated. Sometimes this finely tuned system can go haywire.
Oh, I sense a plot twist coming.
You could say that.
What happens when things go wrong with VEGFA?
Well, sometimes VEGFA production gets out of whack. It's not as tightly controlled as it should be.
Okay, and what happens then?
Well, this dysregulation can lead to all sorts of problems, including diseases.
Diseases like what?
One of the biggest ones is cancer.
Cancer. Wow, that's serious.
Cancer is a major health issue, and VEGFA plays a key role, unfortunately.
Okay, so everyone knows someone who's been affected by cancer, so this is definitely something our listeners need to understand.
Absolutely. In cancer, tumors need a constant supply of oxygen and nutrients to grow and spread.
Makes sense they need to fuel their growth somehow.
Right, and they essentially hijack the body's natural processes to do this, and VEGFA is a key player in this hijacking.
So you're telling me this one molecule is responsible for building blood vessels that heal us. BUT also helps tumors grow.
It's a double-edged sword.
It's wild.
So the tumor cells release signals that stimulate excessive VEGFA production.
Okay.
And this leads to the formation of new blood vessels that feed the tumor.
So it's like VEGFA is unwittingly becoming an accomplice to the tumor's growth.
You could say that this process is known as tumor angiogenesis, and it's a hallmark of cancer development.
Tumor angiogenesis, got it. So the tumor basically tricks the body into helping it grow.
Pretty much.
Are there any other diseases where VEGFA plays this kind of negative role?
Yes, another significant one is age-related macular degeneration, or AMD.
AMD, that's a leading cause of vision loss, right?
Yes, it is. And unfortunately, it's becoming more common as people age.
Okay, so how does VEGFA contribute to AMD?
Well, in AMD, there's excessive VEGFA in the eye.
In the eye.
And this leads to abnormal blood vessel growth in the retina.
The retina, that's the part at the back of the eye that senses light, right?
Exactly. And these abnormal blood vessels can leak fluid and blood.
Oh, that doesn't sound good.
It's not good at all. It damages the retina and ultimately impairs vision.
So it's like those extra blood vessels are interfering with the retina's ability to do its job.
Precisely, they're causing chaos back there.
So VEGFA is a bit of a double-edged sword, essential for life, but also capable of causing some serious problems.
That's a great way to put it.
This is all starting to feel pretty heavy.
I know it's a lot to take in, but the good news is that scientists are working on ways to fight back against VEGFA's harmful effects.
Okay, Few. Tell me more about these countermeasures.
Scientists have been working tirelessly to develop treatments that target VEGFA and its signaling pathways.
So they're trying to find ways to control this powerful molecule.
Precisely. And there have been some remarkable breakthroughs, particularly in the fight against cancer and AMD.
Okay, that's a glimmer of hope. So how do these treatments actually work? Do they just shut down VEGFA completely?
Well, not quite. Remember, we need VEGFA for normal bodily functions.
Right, shutting it down completely would be like turning off the water supply to the whole house.
Exactly. You'd create a whole different set of problems.
So the goal is to find a way to target the bad VEGFA while leaving the good VEGFA alone.
It's all about targeted therapies that disrupt the harmful effects while preserving the essential roles.
That sounds like a delicate balancing act.
It is, but scientists are making incredible progress.
So what are some of the approaches they're taking?
There are two main types of therapies: monoclonal antibodies and soluble receptors.
Monoclonal antibodies and soluble receptors. Okay, those are some big words.
I know, but think of them like tiny blockers designed to interfere with VEGFA's ability to do its job.
So they're like tiny wrenches gumming up the works of those rogue VEGFA molecules.
That's a great analogy. Monoclonal antibodies are like guided missiles they bind to and neutralize specific VEGFA molecules.
So they take them out of commission.
Exactly. They prevent them from interacting with the receptors on cells, basically shutting down the signal for angiogenesis.
Okay, and what about soluble receptors? How do they work?
Think of them as decoys.
Decoys.
Yeah, they mimic the natural VEGFA receptors, but instead of being attached to a cell, they float around freely intercepting VEGFA molecules before they can reach their target.
So they're like setting up a trap to capture those rogue VEGFA molecules.
Precisely.
Wow, that's pretty clever.
These therapies have shown real promise in treating certain cancers and slowing the progression of AMD, giving hope to countless patients.
That's amazing. So we have these tiny blockers that can help fight back against the harmful effects of VEGFA.
It's a game changer.
But I'm guessing it's not all smooth sailing. What are some of the challenges with these therapies?
Well, one of the biggest challenges is drug resistance. Some tumors can find ways to evade these treatments and continue growing.
Ugh, so it's like a constant arms race between the treatment and the tumor.
Exactly. Scientists are always trying to stay one step ahead.
Are there any other challenges?
Another challenge is managing potential side effects.
Side effects.
Yeah, interfering with VEGFA can sometimes disrupt those normal bodily functions we talked about earlier, like wound healing.
Right, because VEGFA is so important for those processes.
Exactly. It's a delicate balancing act, finding the right dosage and treatment strategy to maximize benefits while minimizing risks.
It sounds like there's still a lot to learn and refine when it comes to anti-VEGFA therapies, but it's incredible how far we've come in understanding and targeting this complex molecule.
It's been a remarkable journey of discovery.
And we're not done yet. This is where we'll wrap up part 1 of our deep dive.
There's so much more to explore.
We've covered a lot of ground from the basics of what VEGFA is and how it works to its roles in both health and disease, and we've even explored the exciting possibilities of anti-VEGFA therapies. But there's still so much more to uncover.
We'll delve deeper into the intricacies of VEGFA signaling.
The signaling pathways.
Exactly, and we'll unravel the mysteries of its different isoforms and examine its role in specific diseases in more detail.
So much more to learn.
Join us for part 2, where we'll continue our exploration of this fascinating and powerful molecule.
We'll see you there.
Welcome back to our deep dive into the world of VEGFA.
Still processing everything from part 1.
A lot to cover.
Yeah, it's like VEGFA is this tiny little molecule, but it's doing so much.
Powerful little guy.
It builds blood vessels, it helps regulate oxygen, and then it can go rogue and cause trouble.
A real paradox.
It is fascinating, though. Okay, so in part 1, you mentioned something about VEGFA signaling, like the actual mechanics of how it works. I'm ready to geek out on that. Break it down for me.
All right, let's zoom into the cellular level.
Okay.
Remember those VEGFA receptors we talked about?
Yeah, vaguely.
Those are key for transmitting the VEGFA signal into the cell.
So they're like the antennas picking up the VEGFA signal.
Yeah, good analogy. Think of it like a lock and key system.
Okay, so VEGFA is the key. It binds to its receptor, the lock, and that unlocked something inside the cell.
Exactly. That binding triggers a whole cascade of events inside the cell.
A cascade of events. Okay, so what kind of events are we talking about?
Well, first you got to know there are actually 3 main types of VEGFA receptors.
3 different receptors.
Yeah, VEGFR1, VEGFR2, and neuropilin-1.
Catchy names.
Right. And each receptor has a different affinity for the various VEGFA isoforms.
Okay, remind me what an isoform is again.
Remember those different outfits VEGFA can wear?
Oh, yeah, right. The different versions of the protein?
Exactly. So some receptors are more attracted to certain isoforms than others.
So it's not just about VEGFA binding to, ow, my receptor. It matters which receptor it binds to.
You got it. Each VEGFA isoform has its preferred receptor, and that connection triggers a unique chain of events inside the cell.
So it's like dialing a specific phone number. Each receptor is a different line leading to a different department.
Perfect analogy.
Okay, I'm starting to see how this allows for such precise control over angiogenesis. It's like a customized approach.
Exactly. The body can fine-tune the process depending on what's needed.
Okay, let's talk more about those different VEGFA isoforms. What makes them so unique, and why does the body need so many variations?
Well, it's all about having the right tool for the right job. Remember VEGFA 165, the superstar isoform?
A Beyonce of VEGFA.
That's the one. So it's a master multitasker. It can bind to both VEGFR1 and VEGFR2.
2 different receptors.
Wow. And this triggers different signaling pathways inside the cell. These pathways are what promote the growth and movement of those endothelial cells that line blood vessels.
So it's like VEGFA 165 has this whole toolkit for building and remodeling blood vessels.
You got it. But here's where things get even cooler. Some isoforms, like VEGFA 121, are freely diffusible.
Freely diffusible, what does that mean?
It means they can spread easily throughout tissues, acting like long-range messengers.
Oh, so they can travel far and wide, influencing cells in different locations.
Precisely. In contrast, isoforms like VEGFA 189 are more tightly bound to the extracellular matrix.
The extracellular matrix, what?
It's like the scaffolding that surrounds cells, so these isoforms act more like short-range signals influencing cells in their immediate vicinity.
Okay, so we have long-range messengers and short-range influencers all working together to build and maintain our blood vessel network.
It's a complex and beautiful system.
It is. But why go through the trouble of creating all these variations? Wouldn't it be simpler to just have one type of VEGFA that does it all?
Well, think about it. Different tissues and organs have unique needs when it comes to blood vessel growth.
Okay, I see your point.
A delicate organ like the eye wouldn't need the same type of robust blood supply as a muscle, right?
Right, that makes sense. Like building a house, you wouldn't use the same materials and techniques for every single room.
Exactly. By having a variety of VEGFA isoforms, the body can fine-tune angiogenesis to meet the specific needs of each tissue.
It's like a perfectly choreographed dance with all these different players working in harmony.
A beautiful analogy.
But as we learned in part 1, this elegant dance can sometimes get disrupted, especially in diseases like cancer.
Unfortunately, that's true.
Let's shift our focus now to the role of VEGFA in cancer. We know it helps tumors grow, But how W exactly does that happen?
Okay, so remember how tumors are these rapidly growing masses of cells?
Yeah, they're like out-of-control construction projects.
Exactly. And as they grow, they need more and more oxygen and nutrients to fuel that growth.
Makes sense. They got to eat too.
Right, but the problem is they quickly outgrow their blood supply.
So they're like a city that's growing too fast for its infrastructure.
That's a great way to put it.
Yeah.
So this creates an environment where there's not enough oxygen. Remember hypoxia.
Hypoxia, the low oxygen situation.
And hypoxia triggers the production of HIF-1, which then ramps up VEGFA production.
Right. It's like a desperate plea for more blood vessels. More.
Exactly. The tumor cells are basically screaming, we need more oxygen, we need more nutrients.
And VEGFA is their answer.
Unfortunately, yes, the increased VEGFA levels stimulate the formation of new blood vessels, which provide the tumor with the oxygen and nutrients it needs to grow and spread.
So it's like the tumor is hijacking the body's natural healing mechanisms for its own evil purposes.
That's one way to look at it.
It's pretty sneaky.
It is, and it's not just about providing nutrients. The new blood vessels that form in tumors are often abnormal and leaky.
Leaky blood vessels, what does that mean?
It means they have gaps and weak points.
Oh no.
Yeah, this allows tumor cells to easily escape into the bloodstream and travel to other parts of the body, leading to metastasis.
Metastasis, that's when the cancer spreads, right?
Exactly. So VEGFA is playing a role in both tumor growth and metastasis.
This is getting scary.
I know, but remember those anti-VEGFA therapies we talked about?
Yeah, the tiny blockers.
Those are showing promise in fighting back against these processes.
Okay, so how do they help in this situation?
Well, the goal is to disrupt the tumor's blood supply by targeting VEGFA.
So basically cutting off the tumor's food and oxygen supply.
Precisely, those monoclonal antibodies and soluble receptors can help prevent the formation of those leaky blood vessels, essentially cutting off the tumor's lifeline.
I see it's like cutting off the enemy's supply lines in a war.
A good analogy.
But wait, if VEGFA is so important for wound healing, how do those anti-VEGFA therapies affect that? I'm worried about the potential downsides.
That's a great question, and it's something scientists are very mindful of.
Because we don't want to hinder the body's ability to heal.
Exactly. While anti-VEGFA therapies have shown great promise in treating cancer, they can sometimes have side effects like delayed wound healing.
Okay, that makes sense.
It's all about finding the right balance, disrupting the harmful effects of VEGFA while minimizing the impact on those essential processes.
That's tricky.
It is, but researchers are constantly working to refine these therapies, making them more targeted and effective with fewer side effects.
So it's a constant process of improvement.
It is. Science is always evolving.
This brings me to another point you mentioned earlier, those different VEGFA isoforms. Could we potentially target specific isoforms that are involved in tumor growth while leaving the others untouched?
That's a great question, and it's one of the exciting avenues researchers are exploring.
So instead of targeting all VEGFA, we could just target the bad guys.
Exactly. If we can pinpoint the specific isoforms that are most active in tumor angiogenesis, we might be able to develop drugs that block them, selectively sparing the isoforms involved in essential processes.
That would be amazing.
It would be like using a scalpel instead of a sledgehammer.
Much more precise.
Precisely, but I know you're thinking cancer is incredibly complex and tumors are notorious for finding ways to resist treatment. What about drug resistance?
Yeah, that's a big concern. How are scientists tackling that challenge?
Well, drug resistance is a major hurdle, and scientists are using a variety of strategies to overcome it.
Like what?
One approach is to combine different anti-VEGFA therapies, hitting the tumor with multiple weapons at once, making it harder for it to develop resistance.
Oh, so it's like a multi-pronged attack, giving the tumor less room to maneuver.
Exactly. Another approach is to combine anti-VEGFA therapies with other types of cancer treatments like chemotherapy or immunotherapy.
So hitting it from all angles.
Exactly. The idea is to overwhelm the tumor's defenses.
Okay, that makes sense. Strength in numbers.
It's all about finding the most effective ways to fight back against this formidable foe.
Cancer is a tough opponent, but it sounds like scientists are developing some powerful weapons.
They are. But let's shift gears for a moment and talk about another disease where VEGFA plays a role, age-related macular degeneration, or AMD.
AMD, yeah, we talked about that briefly in part 1. You mentioned that excessive VEGFA activity in the eye contributes to vision loss.
Yeah.
Can you walk me through how that happens?
Sure. So the problem in AMD lies in the macula.
The macula.
That's the central part of the retina responsible for sharp central vision, the kind we need for reading and recognizing faces.
Oh, so that's why AMD affects central vision.
Exactly. And excessive VEGFA in the eye leads to abnormal blood vessel growth in the macula.
And those abnormal blood vessels are leaky.
You got it, and that's where the trouble starts.
Because that leaking fluid can't be good for the delicate retina.
It's not good at all. It causes damage to the sensitive photoreceptor cells in the macula.
And those photoreceptor cells are what allow us to
Precisely so. This damage ultimately leads to blurry or distorted central vision.
So it's like a domino effect. Excessive VEGFA triggers this cascade of events that ultimately leads to vision loss.
It's a complex process, but that's the basic idea.
So how do doctors use those anti-VEGFA therapies to treat AMD? Is it the same approach as with cancer?
It is. The goal is to inhibit VEGFA activity and slow the progression of the disease.
Okay, and how do they do that?
Well, they inject those tiny blockers, the monoclonal antibodies or soluble receptors, directly into the eye.
Directly into the eye. Wow, that sounds intense.
It is, but it's a very effective way to deliver the treatment right where it's needed.
So it's like delivering those targeted weapons right to the battlefield in the eye.
A great analogy. Those treatments have been a game changer for many people with AMD, helping to preserve their vision.
That's amazing. It's incredible how the same molecule can be involved in such different diseases, yet the same basic principles of targeting VEGFA can be applied.
It speaks to the power of understanding the underlying biology.
It really does. Okay, so we've covered a lot of ground in this part one. We've explored the intricate world of VEGFA signaling its role in cancer and AMD, and the promising advancements in anti-VEGFA therapies.
But there's still more to come.
There is.
In Part 3, we'll explore the cutting-edge frontiers of VEGFA research, from its potential in regenerative medicine to the ethical considerations surrounding its use.
Okay, now we're talking sci-fi stuff.
We'll delve into the challenges and opportunities that lie ahead in harnessing the power of this remarkable molecule.
I can't wait. It's clear that VEGFA is a fascinating and powerful molecule with far-reaching implications for human health.
It is, and we're only just beginning to understand its full potential.
This is where we'll wrap up Part 2 of our deep dive.
Join us for the final chapter of our VEGFA adventure in Part 3.
We'll see you there. Back again for the final part of our VEGFA deep dive.
Can you believe how much there is to say about this one molecule?
Seriously. From blood vessels to cancer to AMD, it's like the Swiss Army knife of molecules.
Oh, good enough.
But we're not done yet. You mentioned something in Part 2 about regenerative medicine.
Yeah?
Like repairing or replacing damaged tissues and organs. That sounds like something straight out of a sci-fi movie.
I know, right? But the future is now.
So tell me, how can we actually use VEGFA to regenerate tissues?
Well, think back to how VEGFA orchestrates the growth of new blood vessels.
Okay.
That ability is absolutely essential for tissue regeneration.
Oh, right, because new blood vessels would bring in all the oxygen and nutrients those damaged tissues need to repair themselves.
Exactly. So scientists are looking at ways to deliver VEGFA directly to injured areas or stimulate the body's own production of VEGFA to kickstart the regeneration process.
So like giving those tissues a little boost to help them rebuild.
That's the idea, and the potential applications are pretty amazing.
Like what? Give me some examples.
Well, imagine treating heart attacks by stimulating new blood vessel growth in the damaged heart muscle.
Wow.
Or repairing spinal cord injuries by promoting nerve regeneration.
Okay, now that's some serious sci-fi stuff coming to life.
It is, and there are areas where this research is already showing promise.
Okay, tell me about those.
One area that's really exciting is wound healing.
Wound healing.
Researchers are working on VEGFA-based therapies to speed up the healing of chronic wounds like diabetic ulcers.
Those could be really tough to treat, so that would be a huge breakthrough.
It would. And then there's the really big question, can we grow new organs using VEGFA?
Okay, is that even possible?
It's getting closer to reality. Scientists are using VEGFA to create 3D scaffolds that mimic the structure of organs.
Scaffolds, like a framework.
Exactly, and then they seed those scaffolds with cells that can grow and differentiate into the desired tissue types.
Wait, so they build a scaffold using VEGFA and then add the right cells to grow a new organ?
Pretty much.
That's incredible.
It is, and these bioengineered organs could potentially be used for transplantation.
Wow, that would be a game changer considering the shortage of donor organs.
It would, but with all this incredible potential comes some serious responsibility.
Right? You can't just mess with something as powerful as VEGFA without thinking about the consequences.
Absolutely. Manipulating VEGFA gives us huge power to influence fundamental biological processes, so we have to be very careful.
So what are some of the things we need to consider as we move forward with this research?
Well, one major concern is making sure everyone has access to these treatments. If we can grow new organs or regenerate tissues, we need to make sure everyone who needs them can get them.
Absolutely. These advancements shouldn't just benefit the wealthy or privileged.
Exactly. Everyone deserves a chance to benefit from these breakthroughs.
What other challenges are there?
We also have to be aware of potential unintended consequences. When you start manipulating complex biological systems, there's always a chance of unforeseen side effects or long-term risks.
It's like that old saying, every action has an equal and opposite reaction.
Precisely, we have to be extremely thoughtful and cautious in our approach.
So we need to proceed with both excitement and caution.
Absolutely open and honest discussions involving scientists, ethicists, policymakers, and the public are crucial.
We need all hands on deck to make sure these technologies are used for good.
Exactly. These are powerful tools, and we need to use them wisely.
This has been an incredible deep dive into the world of VEGFA. So much to learn and so much potential.
It's a truly remarkable molecule.
It is. Before we wrap up, what's the one key takeaway you want our listeners to remember?
I want them to remember that VEGF-A is a testament to the power of nature and the ingenuity of science. As we continue to learn more about it, we have the potential to revolutionize medicine and human health.
Absolutely. Well, thank you so much for guiding us through this fascinating journey. It's been an eye-opener.
It's been my pleasure. Thanks for having me.
And to our listeners, thank you for joining us on the deep dive. We'll see you next time for another deep dive into the world of science.